Hello physics students, welcome to video 6 in gravity, where we'll talk about satellite orbits, the types of satellites orbits, and space junk. Now there's a whole lot of different types of satellite orbits. The main ones that you're going to encounter are the geostationary ones, and perhaps some of the low Earth and the polar ones. And we'll go through those fairly quickly. So this is their relative position to each other. The low altitude ones are quite low, obviously, and they're medium altitude, and these are high altitude ones as well. Not drawn to scale, but we'll be hopefully doing a prac where we'll get to see all these satellites in real time. Now the geostationary satellites have to be over the equator, and they have to have a period of 24 hours. They have to rotate around their orbit at the same rate at which the Earth rotates around its axis. And for that reason, they have to be over the equator. Now, being over the equator means that they have a footprint, but they don't cover the polar regions very well, and you have to use other satellites to cover the polar regions. If you look on your neighbour's house or your own house, if you've got a satellite pay TV dish, you'll see that in Tasmania it's pointing at a low angle to the north, and that dish is actually pointing to the satellite, which is over the equator. If you go further north through Victoria, New South Wales and Queensland, you'll see that the satellite dishes point more and more directly up into the sky, because again that same satellite is sitting over the equator. Now because the period is 24 hours, that gives us a couple of constraints about geostationary satellites. Now we know that the centripetal force that's causing the circular motion is provided by gravity, and we have these equations, and we've gone through this before. We're just going to show you why the period of 24 hours, what effect that has at the altitude of the satellites. So we substitute in for V 2 pi r on t, and then we do a bit of maths, we cancel a few things out. You can pause this if you want. You cancel the masses of the satellite out, because little m is the mass of the satellite, big M is the mass that we're orbiting around, and we get to this stage, which should be familiar to us because it's Kepler's third law, and we're told that that is the ratio for any satellite in this system. And if we rearrange it a bit more, we can see that we actually have lots of constants. G is a constant, the mass of the Earth is a constant, 4 pi squared is a constant. And so if the period is a constant 24 hours in seconds, it means that the radius must also be a constant. And it comes out to be 36,000 kilometers approximately of altitude. So all geostationary satellites have to be put in that position, and they have to be over the point of the equator that they're interested in. And they don't move off that point. Whoops, I need to draw a diagram. That's what I needed to do. And so let's make this. If this is the Earth, okay, and that's the equator, geostationary satellites will orbit around the equator. That's a three-dimensional diagram. Yep. With the center of their orbit being the center of the Earth's mass. That's because of the centripetal force has to always point towards the center of the circle, and because gravity is providing it, it has to point towards the center of the mass that's providing that centripetal force. And that's why you can't have a satellite orbiting like this in a circle above the pole, because even though that's the center of the circle, because gravity is providing it, the gravity is always pointing towards the center of the circle, and clearly that's not a stable orbit. That's why they have to be over the equator. Now, did I miss one? No. That's the low Earth orbit, going around faster than the Earth's rotation, and so it revisits the same spot over and over and over again. We can have polar ones. Now the polar ones will see the whole Earth eventually with a few orbits, because the Earth is rotating underneath the actual satellite, and this is a trace of it. Elliptical orbits are like this, and these are used with GPS and other sensing ones, where they can go out to have a wide view and then come in for a close view and do all sorts of different things. Now this is an example where they're trying to show how crowded space is, and it is quite crowded. There are some organisations that actually track all the satellites in real time, and these are real satellites, and they've put a little symbol there which is significantly bigger than the real satellite, but it just shows you how many satellites are sitting around, and these are just the low Earth orbit ones. If you panned out, you'd see a whole lot of more satellites doing all sorts of other things as well. Now why is that important? Well, we've just about come to our limit of how many things that we can put into space, because we've made a bit of a mess of space, and there's a few problems in putting satellites into space because they're going to get interacted with space junk. And this is what can happen, is you can have impacts, and this is on something like this. This would be, I think, the Hubble telescope, and this is an impact. Now these are the impacts on the on a section of the Hubble, and you can see all these arrows represent impacts. Now a lot of these impacts are from dust particles that are in space anyway. They were in space before humans went up there, because they're what would be meteors, and they'll burn up in the Earth's atmosphere. But these are above the Earth's atmosphere, so they actually impact, and most of these are not much of a problem, because people have designed to be capable of withstanding that. But sometimes the impacts can be quite powerful, and this is one that nearly pierced the pressure cell in the International Space Station. And if it had punctured this pressure cell, all the oxygen would have leaked out, perhaps not catastrophically, but it would have been a very dangerous situation for the astronauts, obviously. And some of these impacts can be natural ones, like dust and rock particles that are drifting through space and from the asteroid belt. But nowadays they're getting more and more impacts that are from man-made objects that we've left in space. And we're leaving lots. Like if you think of all the pictures or the films of the rocket stages in the Apollo blowing up and separating as they made their way to the moon, each of those separations there was explosive bolts that blew themselves apart. They're now space junk, basically. And every time you launch something, there's explosive bolts and different ways of breaking things apart, and it's all making a lot of basically litter. And in the early years, people weren't worried about it. They just wanted to have successful missions. But nowadays, it's getting so crowded up there, and all these satellites are worth mega bucks. People are getting worried about it. And so they send up tiles to actually record the impacts, and this would be an example of all the little micro impacts that occur. And this is the apparatus they use. There is a famous story of the space shuttle. One of the space shuttles returned to Earth, and they were looking over it, and they noticed a crack in the windshield. The windshield's about 3 inches thick, and so they took the windshield out and looked at this crack, and they determined that the crack was caused by a speck of paint. A speck of paint that had been travelling so fast that it actually had burrowed its way 2/3 of the way through that glass, because it had such a huge velocity. And that paint was from some previous happening in the Earth's atmosphere, or the Earth's upper atmosphere, from a space program or a satellite launch or something. And so it can be quite dangerous. Now, lots of times stages of rockets and various other things are returned to Earth, and they usually burn up, but they don't always, so it can actually be a problem on the surface of the Earth, but to a less extent. It's only really big items that manage to return to the surface of the Earth. Now, a lot of the debris comes from a number of incidents. In 2007, China blew up one of its satellites just to prove that it had missiles that could blow up satellites, sort of a defensive thing, because remember, some of the satellites up there are top secret military ones from different countries, and not all countries are happy that they're being spied on by other countries' satellites. And so China just showed that it could blow up a satellite. But it was a very reckless thing, because it made a huge amount of debris that is now impacting on everybody's satellites, including China's. In February 2009, 2 satellites collided. Because there's so many satellites, people can't predict how their orbits are going to interact, and not all satellites are positioned perfectly, and not all satellites maintain their same orbits and are monitored as such. And in this case, 2 satellites collided, made a massive plume of materials that's still orbiting around the Earth. In 2011, the International Space Crew actually had to take shelter in one of their escape capsules because the radar trackers had located some space debris that was coming towards them. And most recently, as this month, or in March 2015, an old US satellite blew up, most likely due to a power failure, and it didn't make a huge amount of mess because it was a low impact explosion, and so most of the chunks aren't travelling very fast. But it's still a problem. It's all adding to the amount of junk up there. Now on our OneNote there'll be some videos where you can watch. One is about the Chamber of Horrors, where at NASA they test satellites. They test satellites before they get launched, and another one about how they go about making a satellite and testing a satellite and all the processes involved. Quite interesting if you're into that sort of thing. And in the next video we're going to look at gravitational fields and gravitational field strength. So, cheerio.